Electricity is everywhere. It hums behind walls. It flows through cables under oceans. It powers cities, phones, hospitals, and satellites. Every second, it keeps the modern world alive. Yet most people do not truly know what it is. They know how to use it. They depend on it. But the real nature of electricity remains hidden, even to many who study it for years. That mystery is where this story begins. For over a century, electricity has been explained using simple comparisons. Water flowing through pipes, particles rushing through wires. These explanations sound clear and comforting. They give the feeling of understanding, but that feeling is often false, because when the details are examined closely, the story starts to break apart. Electrons move far slower than people expect. Energy does not travel where most textbooks say it does. And the moment a switch is flipped, something strange happens that challenges common sense. This confusion is not limited to beginners. Even trained engineers often rely on rules that work without fully grasping why they work. Equations give correct answers, but equations alone do not explain reality. They describe behavior, not meaning. This gap between calculation and understanding is where electricity becomes unsettling. It works perfectly, yet resists simple explanation. That tension has existed since the earliest experiments with sparks and charged glass. In the middle of this confusion stood Richard Feynman, a physicist known not just for intelligence, but for clarity. He did not accept explanations that only sounded right. He questioned the metaphors everyone else used. He challenged the idea that understanding meant repeating familiar words. To him, true understanding meant seeing what nature was actually doing, even if the answer felt uncomfortable or incomplete. Feynman was involved in some of the most important scientific work of the 20th century. He helped shape quantum mechanics. He played a role in the development of nuclear physics. He advised on space missions. Yet one of his greatest talents had nothing to do with advanced math. It was his ability to explain basic ideas without lying about their complexity. He refused to oversimplify if it meant distorting the truth. When Feynman spoke about electricity, he did something unusual. He did not try to make it feel easy. Instead, he made it honest. He showed why common explanations fail. He revealed where the mystery actually lives. And in doing so, he gave people a deeper kind of understanding, one that stays long after the equations are forgotten. In this video, you will learn why electricity does not behave the way most people think it does. You will learn why electrons are not the main carriers of energy in a circuit. You will learn where the energy really flows, and why that fact surprises even professionals. You will learn how electric fields shape space itself, and why flipping a switch changes more than just a wire. These ideas are rarely explained clearly, yet they change how everything fits together. You will also learn something deeper than physics. You will see how Feynman approached knowledge itself. He believed that confusion was not a failure, but a starting point. He believed that saying "I do not know" was more honest than repeating an answer that sounds correct. That mindset is part of why his explanations still matter today. There is a moment in understanding electricity when familiar ground disappears. The wire stops being the center of the story. The flow stops looking like motion. Space itself becomes active. Energy moves without visible matter racing along. This moment can feel unsettling, but it is also freeing. It replaces memorized models with insight. That is the moment this video is building toward. Along the way, lesser-known facts will surface. Ideas that are often skipped in classrooms. Details that textbooks mention briefly, then move past. Historical misunderstandings that shaped how electricity was taught for generations. These details matter because they explain why confusion persists and why Feynman's approach stood out so sharply. This is not a video about formulas. It is not about solving problems on paper. It is about seeing electricity as it truly behaves, not as it is usually described. By the end, a light turning on in a room will not feel quite the same. The simple act of charging a phone will carry a new meaning. The invisible will feel closer. Not because it became simple, but because it became clearer. The reason to watch until the end is simple. The final idea ties everything together. Without it, electricity remains a set of disconnected facts. With it, the pieces lock into place. Feynman believed that understanding should feel like recognition, not memorization. That feeling comes only when the full picture is revealed. This channel exists for that exact reason. To explore ideas that shape the world without flattening them into shallow explanations. To slow down where others rush. To respect complexity without turning it into confusion. If that kind of understanding matters to you, then you are in the right place. Welcome to the channel. If you enjoy learning how the hidden parts of reality actually work, consider subscribing and staying with us. More stories like this are coming, and each one looks beyond the surface to find what is really there. For most people, electricity is explained in a very familiar way. Next, it is described as something that flows, like water moving through a pipe. The wire becomes a narrow channel. The battery becomes a pump, and electrons are treated like tiny particles rushing forward, pushing energy along as they go. This explanation appears in classrooms, textbooks, and casual conversations. It sounds reasonable. It feels intuitive. And because it works well enough for simple problems, it rarely gets questioned. This picture becomes even stronger when diagrams are introduced. Arrows show direction. Lines show paths. Everything appears clean and controlled. The idea suggests that when a switch is turned on, electrons pour out of one end and race toward the other. The faster they move, the more power is delivered. The longer the wire, the longer the journey. It feels like common sense applied to something invisible. But this mental model quietly creates confusion. If electrons are truly racing through the wire, then speed should matter in obvious ways. Distance should cause delay. A long wire should take time to deliver energy. Yet when a light switch is flipped, the bulb turns on almost instantly, even if the wire stretches across a building. That instant response does not fit the picture of slow-moving particles traveling from one end to the other. Another problem hides in scale. Electrons do move, but their actual drift is incredibly slow. In many household circuits, an electron may take minutes or even hours to travel a few centimeters. This clashes sharply with the idea of rapid flow. If electricity worked like water in a pipe, nothing should happen quickly at all. The familiar explanation starts to bend under its own weight. Still, the water model survives because it gives comfort. It replaces an abstract idea with a physical one. It allows people to feel like they understand what is happening, even when important details are missing. That sense of understanding becomes a barrier. Once the picture feels right, there is little motivation to look deeper, even when reality behaves in ways the picture cannot explain. When real measurements are taken, the water analogy begins to break down. Electrons inside a metal wire do move, but their motion is nothing like a fast current rushing through a pipe. They drift slowly, pushed by electric forces, colliding constantly with atoms in the metal. Their average speed is so low that it is difficult to reconcile with everyday experience. This is not a minor detail. It sits at the center of the misunderstanding. At the same time, electrical effects appear almost instantly. A lamp turns on the moment a switch is flipped. A motor begins to spin without delay. The distance between the power source and the device seems to make no difference. Whether the wire is short or long, the response feels immediate. This alone should raise questions. Slow-moving particles cannot explain fast results. The usual response is to adjust the story. It is said that while electrons move slowly, the signal moves fast. This explanation helps, but it often remains vague. What exactly is moving, if not the electrons themselves? What carries the energy from one place to another? The water analogy offers no clear answer here, because in water systems, the fluid itself is the carrier. In an electrical circuit, energy behaves differently. It is not tied to the physical travel of particles along the wire. Instead, it is connected to changes that spread through the system as a whole. When a switch closes, conditions throughout the circuit shift. Forces appear. Fields adjust. The response is not delayed because nothing needs to travel the entire length first. This behavior feels unfamiliar because it does not match everyday experiences. There is no visible substance flowing from one end to the other. The action happens through relationships, not transport. Cause and effect are linked through space itself. The wire becomes part of a larger interaction rather than a simple channel. As this deeper behavior starts to emerge, the comfort of the water model fades. It becomes clear that electricity is not just a moving substance. It is a coordinated response, shaped by invisible structures that exist even before anything is turned on. Feynman approached electricity by stripping away the comforting stories and focusing on what physics actually describes. He pointed out that electricity is not primarily about things moving through wires. It is about fields. An electric field is not a metaphor or a mathematical trick. It is a real structure that exists in space. In a metal wire connected to a power source, this field is already present, shaped by the charges inside the material and the conditions around it. Before any switch is flipped, the wire is not empty or inactive. Charges are arranged, forces are balanced. The electric field exists in a stable form, extending through the wire and into the space around it. Nothing dramatic is happening yet, but the system is prepared. This detail is often overlooked because fields cannot be seen and their presence does not announce itself until something changes. The moment the switch is closed, the arrangement shifts. The electric field adjusts throughout the circuit. This adjustment does not wait for electrons to crawl from one end to the other. It spreads at a speed determined by the properties of space and the materials involved. The change moves rapidly, establishing new forces everywhere along the wire almost at once. It is this changing field that transfers energy. Energy is carried by the structure of the field as it reconfigures itself. The electrons respond locally. They shift slightly, they bump into atoms, and they generate heat or light. But they are not the messengers traveling long distances with packets of energy in their hands. They are participants reacting to instructions delivered by the field. Feynman emphasized that focusing on electron motion misses the main event. The important action is happening in the invisible pattern that fills the circuit. The wire guides this pattern, but it does not contain it in a simple way. Space itself becomes active. Once this perspective is adopted, many confusing details begin to make sense, even though the process remains subtle and counterintuitive. Once the focus shifts to electric fields, the role of electrons becomes clearer and more modest. Electrons are not racing through wires at high speed, carrying energy from one device to another. Instead, they move slowly, almost reluctantly. Their motion is more like a gentle drift than a rush. They are surrounded by atoms in the metal lattice, constantly colliding and changing direction, never gaining much ground. What drives their motion is the electric field. When the field changes, each electron feels a force at its own location. It does not need to know what is happening far away in the circuit. It only responds to the conditions right where it sits. This local response is enough. When every electron reacts at nearly the same time, the combined effect becomes powerful and immediate. A useful way to think about this is as a coordinated response rather than a journey. Each electron shifts slightly, passing influence to its neighbors through electric forces. No single electron travels far, but the disturbance moves quickly through the system. The effect spreads because the field connects everything at once, not because particles are traveling long distances. This is why electrical devices respond so fast. The speed comes from the field, not from the electrons themselves. The electrons act more like intermediaries. They convert the field's instructions into physical effects. They heat filaments. They emit light. They push against magnetic forces in motors. Their small movements add up to visible outcomes. Seen this way, electrons are essential but not heroic. They do not carry energy across the circuit like couriers. They are more like a crowd responding to a signal. Each person moves only a step or two, yet the signal passes through the entire line almost instantly. The wire provides the structure, the field provides the command, and the electrons simply follow along, doing their part without ever traveling very far. One of the most surprising aspects of electricity appears when the path of energy is examined more closely. Intuition suggests that energy should travel inside the wire, carried along by moving charges. The wire feels solid and important, so it seems natural to assume that everything of value happens within it. Yet careful analysis shows a different picture, one that places the wire in a supporting role rather than a central one. The energy associated with an electric circuit actually moves through the space around the wire. It travels in the electromagnetic field that surrounds the conductor, not inside the metal itself. The wire shapes this field and guides it, but it does not contain the energy in the way a pipe contains water. The space around the wire is active, filled with interacting electric and magnetic fields that work together to transport energy. This idea feels unsettling at first. Empty space is usually treated as nothing, a background where real things happen. In electricity, that background becomes the main stage. Energy flows through space, hugging the wire, responding to its shape, but remaining outside the metal. The wire's role is to provide boundaries and conditions that allow the fields to form in a stable way. Experiments support this view in direct and indirect ways. Measurements of energy flow match predictions that place it outside the conductor. Changes in field patterns explain how energy reaches components without requiring particles to travel long distances. These results are not philosophical arguments. They are consequences of tested physical laws. Once this perspective is adopted, familiar objects take on a new character. A simple wire is no longer just a passive connection. It becomes a guide for invisible structures that extend beyond its surface. Space itself carries the action. The circuit includes not only metal and components, but the surrounding environment as well. Energy moves through that extended system shaped by fields that remain unseen but very real. Electricity feels mysterious because its most important parts are invisible. The forces that drive it do not glow, hum, or leave clear traces in the air. Electric fields exist everywhere around charged objects and wires, yet there is no direct sense that can detect them. They do their work silently, shaping motion and transferring energy without ever announcing their presence. What people experience instead are the results. A room fills with light. A wire grows warm. A motor begins to spin. These effects are concrete and familiar. They can be touched, measured, and described. The cause behind them remains hidden, separated from everyday perception. The mind naturally focuses on what it can see, and the unseen source fades into abstraction. This separation encourages misleading stories. When the cause cannot be observed, it is replaced with something that can be pictured. Flowing particles, stored substances, mechanical motion. These ideas borrow from daily experience, making electricity feel more approachable. But they also mask the true process, which unfolds in a realm that does not match ordinary intuition. Even scientific instruments do not show electric fields directly. They reveal consequences, forces on charges, energy transferred to materials, patterns inferred from careful measurements. The field itself is reconstructed through reasoning, not observation. This indirect knowledge can feel unsatisfying, especially when compared to things that can be seen moving from one place to another. The mystery deepens because electricity behaves consistently despite its invisibility. It follows precise laws. It delivers reliable results. Devices work again and again without exposing the mechanism that makes them work. Its reliability creates trust, but not understanding. People accept that it functions, even if they cannot say how. As long as attention stays fixed on outcomes alone, electricity remains distant and strange. The cause continues to operate behind the scenes, shaping reality without stepping into view. The gap between what is experienced and what is happening sustains the sense of mystery that has surrounded electricity since its discovery. Feynman believed that understanding was an active process, not a passive one. Memorizing formulas or repeating accepted explanations did not count as knowledge in his view. Those tools were useful, but they were not the goal. Real understanding meant being able to describe what was happening in simple terms, without hiding behind technical language. If an explanation could not be stated clearly, then it was not truly understood.
He was comfortable admitting uncertainty. When a question reached the edge of what physics could explain, he did not try to decorate the gap with confident words. He accepted mystery as part of reality. This acceptance was not a surrender. It was an honest acknowledgement of limits. For Feynman, pretending to know was far worse than openly saying that something was not yet clear.
At the same time, he had little patience for shallow answers. Explanations that sounded neat but failed under scrutiny bothered him. He challenged ideas that were repeated simply because they were familiar. He pushed past analogies when they stopped being accurate. This attitude often made his explanations feel unsettling, because they removed comforting illusions instead of reinforcing them. Feynman's way of thinking placed curiosity at the center. Curiosity was not just interest, it was a discipline. It required asking why again and again, even when an answer seemed sufficient. It required testing explanations against reality, not against tradition. Curiosity kept ideas flexible and alive, rather than frozen into slogans. In this approach, formulas became maps rather than destinations. They pointed toward relationships, not meaning. The real goal was to see the structure beneath the symbols, to sense how nature behaved, even when the behavior did not align with everyday intuition. This mindset shaped how Feynman talked about electricity and every other subject he touched, pushing understanding beyond repetition and toward insight. Feynman believed that understanding was an active process, not a passive one. Memorizing formulas or repeating accepted explanations did not count as knowledge in his view. Those tools were useful, but they were not the goal. Real understanding meant being able to describe what was happening in simple terms without hiding behind technical language. If an explanation could not be stated clearly, then it was not truly understood. He was comfortable admitting uncertainty. When a question reached the edge of what physics could explain, he did not try to decorate the gap with confident words. He accepted mystery as part of reality. This acceptance was not a surrender. It was an honest acknowledgement of limits. For Feynman, pretending to know was far worse than openly saying that something was not yet clear. At the same time, he had little patience for shallow answers. Explanations that sounded neat but failed under scrutiny bothered him. He challenged ideas that were repeated simply because they were familiar. He pushed past analogies when they stopped being accurate. This attitude often made his explanations feel unsettling because they removed comforting illusions instead of reinforcing them. Feynman's way of thinking placed curiosity at the center. Curiosity was not just interest, it was a discipline. It required asking why again and again, even when an answer seemed sufficient. It required testing explanations against reality, not against tradition. Curiosity kept ideas flexible and alive rather than frozen into slogans. In this approach, formulas became maps rather than destinations. They pointed toward relationships, not meaning. The real goal was to see the structure beneath the symbols, to sense how nature behaved, even when the behavior did not align with everyday intuition. This mindset shaped how Feynman talked about electricity and every other subject he touched, pushing understanding beyond repetition and toward insight. When electricity is reframed through this lens, the entire picture changes. It is no longer useful to think of it as a substance traveling from one place to another. Nothing is being poured, pushed, or delivered in the usual sense. What matters instead are interactions. Relationships between charges, fields, and space itself take center stage. The behavior of the system comes from how these elements influence one another. Electric fields connect charges across distance. They do not wait for particles to arrive before acting. When conditions change at one point in a circuit, those changes reshape the field everywhere else. Charges respond locally, but the coordination comes from the field that links them. This is not motion in the ordinary sense. It is communication through structure. In this view, space is no longer empty or passive. It becomes an active participant. Energy exists in the configuration of fields spread throughout space. As those configurations change, energy flows. The movement is not tied to matter sliding along a path, but the patterns evolving over time. Space carries energy in the same way a stretched surface can carry tension. The wire still matters, but its role is different than most people assume. It does not serve as a container for energy. It acts as a guide that shapes how fields form and how charges can respond. The material of the wire sets boundaries and constraints, allowing certain patterns while preventing others. It influences the flow without being the flow. This reframing replaces a simple but misleading story with a deeper one. Electricity becomes a process rather than a thing. It is defined by interaction, not transport. Once this idea settles in, many puzzling details stop feeling strange. They begin to align with a picture where fields, charges, and space work together as a single system, each playing a role in a quiet, coordinated exchange. Electricity resists being reduced to something simple. Every attempt to compress it into a neat image leaves something important behind. The deeper it is examined, the more layers appear. Fields, forces, space, and interaction all overlap in ways that challenge ordinary thinking. This complexity is not a flaw. It is part of what makes electricity remarkable. There is a quiet beauty in a phenomenon that works perfectly while remaining unseen. Lights turn on. Signals travel across continents. Machines respond with precision. All of this happens through structures that cannot be touched or observed directly. The elegance lies in that hidden order, in the way invisible relationships produce reliable results again and again. Feynman did not try to strip electricity of its mystery. He understood that mystery was not the enemy of knowledge. Instead of pretending that everything could be made intuitive, he showed where the mystery actually lives. Not in ignorance, but in the fabric of reality itself. The mystery was not a failure to understand. It was a feature of how nature operates. By shifting attention away from comforting metaphors and toward real mechanisms, he changed how understanding feels. Confusion became a signal to look deeper rather than a reason to stop. Questions became tools instead of obstacles. The focus moved from memorizing answers to seeing relationships. This perspective alters more than a single topic. It changes how learning itself is approached. Electricity becomes an example of a broader idea, that the world does not owe simple explanations, yet it offers coherence and beauty to those willing to look honestly. Once this way of seeing takes hold, the ordinary world feels different. The wires and walls, the glow of a lamp, the hum of a device all point to something larger and more subtle at work. The mystery remains, but it is no longer distant. It has a place, and knowing where it lives transforms how everything connected to it is understood. Electricity does not become smaller when it is understood this way. It becomes wider. It reaches beyond wires and devices and enters the space around them. What once seemed like a simple flow turns out to be a quiet conversation between fields and charges carried by space itself. That shift in perspective is what Richard Feynman offered. Not an easy answer, but a more honest one. Understanding electricity is not about removing wonder. It is about placing that wonder in the right place. The mystery does not disappear. It becomes clearer, deeper, and more meaningful. Once you see electricity as interaction rather than motion, the everyday world feels richer. The light switch, the charging cable, the power lines outside all hint at an invisible structure doing precise work every moment. If this video helped you see electricity differently, show your support by liking the video. It helps the channel grow and reach more curious minds. And if you enjoy content that looks beneath the surface of how the world works, subscribe to the channel and stay with us. More ideas like this are coming, each one exploring the hidden layers that shape reality.